as we discussed about a balanced three-phase circuits, okay, of course the voltage and load are balanced in terms of magnitude and out of phase with each other by 120 degree. So we have term balanced phase voltage where all phase voltage are equal in magnitude and out of phase with each other by 120, and the voltage will connected to a balanced load where the phase impedance are equal in magnitude and in phase. Okay, so for a phase voltage, okay, the voltage source can be either Y connected or delta connected. Okay, so a phase voltage can be either in Y connected. Okay, we call this as Y connected. Okay, so line A, line B, and line C. So this is BAN, BBN, and BCN. Okay, this is what we call Y connected source. And also we have delta connected source. Okay, this is line A, line B, and line C. So this voltage we call as VAB. Okay, this one is VBC, and this one is VCA. This is what we call delta connected source. Okay, so for a balanced load, we also have Y connected load and delta connected load. Okay, so the phase load can be either Y connected or delta connected depending on the end application. So for Y connected, okay, we have three impedance. Okay, three impedance connecting to line A, line B, and line C. This is for Y connected load. Same as delta connected load. Okay, we also have three balanced load. Okay, and it will connect to line A, line B, and line C. For a balanced Y connected load, where Z1 will equals to Z2 will equals to Z3, or we call it as Z Y connected, where ZY is the load impedance per phase. So, and for a balanced delta connected load, ZA is equals to ZB is equals to ZC, where Z delta is the load impedance per phase in this case. Okay, so you have learned about star and delta transformation in circuit theory 1. Okay, so from this equation, okay, we can transform the delta to Y load or from Y load to delta load, okay, by this equation. Okay, if you want, if you have a Y load and you want to, you need to convert to a delta, so you have to calculate the impedance for Y connected load times with 3. Or if you have a delta connected load and you want the circuit as a Y connected load, okay, you have to multiply with 1/3 times with the delta connected load. Since we have a balanced phase voltage where we have Y connected source and delta connected source, okay, and we also have a balanced load where the balanced load is consist of Y load and delta load. So there is a 4 possible combination or connection for a source and load connection. Okay, so the first one is a Y connected source. Okay, Y connected source, okay, connected to a Y load. Okay, this is what we call a balanced Y circuit. Okay, where a balanced phase voltage, okay, a balanced Y phase voltage connected to a Y load. Okay, we call it as a Y circuit. Okay, the second one is a Y delta. Okay, we have a voltage source uh, in Y connection. Okay, connect to a delta load. Okay, we have Y source connected to a delta load. The third one, when we have a delta source connected to a delta load. Okay, this one is a delta source connected to a delta load. Okay, and the last combination is a delta source connected to a Y load. Okay, this is delta source connected to a Y load. We begin with this balanced Y systems, okay, because any balanced three-phase system can be reduced to an equivalent Y system. And so therefore, analysis of this system should be regarded as the key to solving all balanced three-phase systems. Okay, so a balanced Y system is a three-phase system with a balanced Y connected load and a balanced Y connected source. Okay, so for a balanced Y connection, okay, we have four parameters that you should know, which is phase voltage. Okay, we call this as VAN, VBN, and VCN. You have to remember this. Okay, and line currents IA, IB, IC. So line current is current flow from voltage source to the load. We call it IA, IB, IC regarding their name of lines. Okay, this is line A, line B, and line C. Okay, we also have load impedance. We call it as ZY. Since it is balanced load, so the value of impedance of ZY is equivalent. And we also have line voltage, okay, which is VAB, VBC, and VCA, where the VAB will be calculated from line A to line B, VBC from line B to line C, and VCA from line C to line A. Although the impedance ZY is the total load impedance per phase, it may also be regarded as the sum of the source impedance. Okay, we also have source impedance, okay, line impedance ZL, and load impedance also Z capital L. Okay, we also have in a balanced YY connection. Okay, we also have source impedance at source, line impedance at the line, and load impedance at the load. So the ZY will be calculated as a total impedance per phase. So where ZY is equals to Z source plus Z line impedance and load impedance. Okay. So ZS source impedance is denotes the internal impedance of the phase winding of the generator. Line impedance is the impedance of the line joining a phase of the source with a phase of the load. And load impedance is the impedance of each phase of the load. Okay, basically the source impedance and line impedance are often very small compared with the load impedance. So one can assume that Y load is equals to load impedance if there is no source or no line impedance. Okay, assuming a positive sequence, okay, so the phase voltage, Okay, for a Y connection is VAN, VBN, and VCN. Okay, as we mentioned earlier in a phase sequence, VAN is equals to V peak with 0 degree, both VBN will be out of phase minus 120 degree, and VCN is plus 120 degree. So from there, we can calculate the line to line voltage, okay, VAB, VBC, and VCA. Okay, they are related with the phase voltage. Okay, to calculate VAB, VAB is equals to VAN, okay, VAN minus VBN. Okay, so from the calculation, okay, where VAN is V peak with 0 degree minus to V peak with minus 120 degree. Okay, so the calculation will be V peak 1 plus 0.5 plus J 3 over 2 square root 3 over 2, or we can simplify this one as square root 3 V peak with 30 degree volt. Okay. So similarly, we can obtain for VBC and VCA. Okay, where the angle for VBC and VCA, you should minus 120 and plus 120 degree. So the magnitude of the line voltage is square root 3 times the magnitude of phase voltage. Okay, or we can say that as we say, V lines is equals to square root 3 V peak for a line to line voltage. Okay, since I have told about the magnitude in phase voltage and line voltage, so all the phase voltage and line voltage are equal in magnitude but out of phase of 120 degree. In calculating line currents, we can apply KVL to each phase in figure 12.10. So we can obtain line current as VAN over load Y impedance. Okay, over load impedance or Y impedance. Okay, so you know that current flow from VAN through this line A. Okay, then find through load impedance. So line currents is equivalent to phase voltage. Okay, this one is phase voltage over load impedance. Okay, Y load. Okay, similarly with IB and IC, the magnitude of IB and IC is equal to IA, but the angle is minus 120 degree and plus 120 degree for IC. In our YY circuit, okay, before this I have mentioned about line voltage, phase voltage, okay, phase voltage, line voltage, phase current, and line current. So for a YY connected system, okay, line current, okay, IL, line current, which is IA, IB, and IC, is equals to I phase. It's same as the phase current in a YY system. Okay, we still use single subscript for line currents because it's natural and conventional to assume that line currents flow from source to the load. Okay, so previously we use IA, so we use subscript for IA, IB and IC. So one more thing, so there is an alternative way of analyzing a balanced YY system is to do so on to a per phase basis. Okay, so I have mentioned about a three-phase system. So you can analyze this balanced YY system using a per phase basis. So you can use as a single phase equivalent circuit. So you can read as a reference. This is phase voltage VAN. Okay, connected to a Y load. Okay, this is ZY. Okay, let's say this is line A to line A, from line A to capital A. Okay, this is the neutral line. Okay, so for calculating the line current, okay, IA, okay, so this one is a series circuit. You can see this is a series circuit, and you can see that this you can apply from a KVL, okay, current flow through the one single loop. Okay, so using Ohm's law, okay, you can get the line current IA. So IA equals to VAN over ZY. So to get IB and IC, okay, once you got the value for IA, so you use your the magnitude of IA. Okay. So the angle for IB, okay, from value of IA, so this is angle for IA. Okay, you have to minus 120 degree for a positive sequence. Okay, while for IC, okay, you use the same magnitude of IA, okay, with angle IA, okay, plus 120 degree. Okay, so you use this single phase equivalent circuit to obtain IB and IC. So as long as the system is balanced, so you only need to analyze one phase.